Welcome everybody. My name is Neese and it's my great pleasure and my honor to welcome you to the release event of ORCA 6.1 on behalf of the ORCA development teams at the Max-Planck-Institut for Kohlenforschung in Mülheim an der Ruhr, Germany, and the company FACCTs in Cologne, Germany. Together with our collaborators all around the world, we have tirelessly worked to bring you a better ORCA experience. In fact, it was pretty much a year ago, actually less than a year ago, on July 25th, 2024, when ORCA 6.0 was released. And we were all standing here, we were proud, we were happy, and we were very, very tired. Because for the 3 years prior, we had worked to rebuild the entire ORCA infrastructure. And that was a titanic work, something that probably has never been done. And we made a specific promise on that day. And that promise was that going forward, ORCA development would be much faster because the new infrastructure is so much more powerful and so much more streamlined that it will be a pleasure. And I'm not saying a walk in the park, but it will facilitate further development. And today, I believe with the release of ORCA 6.1, pretty much 11 months after we released ORCA 6.0, I believe we make good on this promise. And in order to show you all of the things that ORCA 6.1 can do and that from today on you can experience yourself, I will give you an overview of what has happened. So please join me in welcoming ORCA 6.1. It will be public today and downloadable in our forum. So the first thing that I will talk about is improvements in mainstream quantum chemistry, and that means the self-consistent field machinery, DFT and Hartree-Fock, analytic gradients, analytic Hessians, and molecular properties. So that is the bread and butter of computational chemistry, and we all do it, like hundreds of thousands of people do it every day. And so the first thing that is noteworthy here is ORCA 6.0 introduced the Lean SCF program. And the Lean SCF program was really a complete rewrite of the SCF engine in ORCA, and it was greatly streamlined in a way that it minimizes the use of memory, because it became evident that as you run large calculations on large molecules on parallel machines, that the usage of the core memory left a lot to be desired in previous ORCA versions. And so Lean SCF was an attempt to fix it. Now we did, and it allowed much larger calculations much more efficiently. But as we went larger and larger and larger and larger, further bottlenecks came up. In fact, Lean SCF was not the bottleneck anymore, but it was ORCA startup that is like organizing the startup task, and ORCA gas that is producing the initial gas orbitals. And so we went back to the drawing board, and particularly Ute Becker was meticulous in finding the last possible byte that can be saved. And she did. And it was very successful. So ORCA 6.1's Lean SCF uses up to 30% less memory than 6.0. And that was instrumental for doing SCF calculations that are, I believe, unprecedented. So what you see here is the Crumb-Bean octamer. So Crumb-Bean was one of the poster childs, and when it was first possible to do SCF calculations on a whole protein, 640 atoms or so, it was spectacular. And in 2013, we did the first couple cluster calculation on Crumb-Bean. It was spectacular. And now what we can do today is to take Crumb-Bean and study an octamer of it, and use a double zeta or even a triple zeta basis set. And the triple zeta basis set has 116,904 basis functions. So that goes well beyond the magic barrier of 100,000 basis functions. And these are calculations that are doable with ORCA 6.1. I'm not saying it's fun to converge such calculations, but they're doable. The program allows to do them, and it will not crash if you give them a sufficiently large computer. So what is on the horizon here is very obviously that you can study protein-protein interactions from first principles electronic structure theory, and even with good competitive basis sets. And I believe that is something that is breaking through a magic barrier and will lead the way into a very bright future for computational chemistry. So, and this is just by paying attention to detail, not by any spectacular new concept. Well, actually, there is one concept that is new, and I'm going to talk about this now. So, in ORCA 6.0, we have given you the fast multiple method for embedding calculations, and that was a very big step forward in allowing large and complicated embedding calculations, such as you have in QMMM or when you study solids. And it didn't stop there, and we were rethinking like how to use multiple approximations in the quantum region. So for the quantum interaction, and in particular it's the Coulomb interaction that naturally scales quadratically. And if you want to make progress, like in terms of the scaling, you need to bring that down to linear, and it's well known that the fast multiple method is the way to do that. But the fast multiple method in its original form, it felt a bit contrived to us. I'm not dissing it. It's wonderful, beautiful work pioneered by Martin Head-Gordon and others that made this possible. But we found a way that we believe is more natural, and we called that the bubble pole algorithm, or BUPO algorithm. And in that algorithm, the main difference to the FMM method is that real space is not partitioned into boxes, but into spheres. And these spheres we call bubbles. And in these bubbles, we collect objects like shell pairs or auxiliary basis functions. And then we make the multiple approximations at the centers of these bubbles, create a bubble hierarchy. And so we come to linear scaling, density fitted Coulomb builds. So the original algorithm in ORCA is the so-called split RIJ method. It was first proposed in 2003, and then it was improved for ORCA 6 and 6.0 in 2021. And it's very stiff competition to beat the split RIJ method, just because it's incredibly efficient. But the BUPO algorithm does, as you see, it's actually linear scaling with respect to system size, and it does have a crossover. Don't get too excited, the crossover is relatively late. Even for linear chains, it does not occur before you have like around 400 atoms. And that means in 3D systems, the crossover with a split RIJ is even later. But it is a high accuracy algorithm. It usually reaches at least microhartree accuracy, and it is linear scaling with respect to system size. It is also based on somewhat new ideas, and that's why it's a very fun algorithm. It is available in ORCA 6.1. Please check it out. The other thing that we did, and that is something that goes very much back to the work of Christian Ochsenfeld and his group for a very long time. They've been studied distance-dependent pre-screening method. And that is based on the realization that the Schwarz pre-screening that everybody is using in their direct SCF solvers, it does not take into account the distances between the two charge clouds that are interaction. So you have base function product here, base function product there, and the Schwarz screening does not know anything about the distance between them. But it's clear that the electron repulsion integral falls off as a function of their distance. And so that means the larger your system gets, the more of these like distant charge interactions you have, and the more the Schwarz pre-screening will underestimate them, meaning that you calculate very many more integrals than you need. And Christian Ochsenfeld and his co-workers, they have proposed a whole series of approximations. Some of them are rigorous upper bounds and some of them are not. but they incorporate their distance dependence. And the latest is from 2017, and that is so-called CSEM estimator, and that is something that we have implemented together with a few other distance dependent estimators. The savings in real life are, at least in our hands, a little limited, but you can save maybe 20 to 30% of computer time if you use a distance-dependent pre-screening on a large molecule. Caveat, it's not yet implemented for the RI approximation, but that is obviously something that we will do at some point. Now, next thing, ORCA 6.0 introduced the delta SCF method, and the delta SCF method is a very powerful tool to converge to alternative electronic configurations in a controlled manner. And the specialist here on the team is Jurek Schmerwitz, and he has done an awesome job improving that method further. So there is a new delta SCF method, the GMF method, and it can be applied to a whole range of physical situations that you may want to study in your own work. And that is, for example, conical intersections, charge transfer excitations, where we know that TD-DFT has big problems, or Rydberg excitations that are also problematic with TD-DFT. So delta SCF is improved and will continue to improve, and it's a very nice method that is a very powerful tool in the arsenal of the ORCA electronic structure toolbox. So let me give you a few more things that have happened in density functional theory since the release of ORCA 6.0. And the first thing, that is an experimental implementation that we give to you to play with, to have fun with. And that is a technique that many of you may not know very well, and that's called analytic density functional theory. And what is behind that is the idea that you can do density functional theory without any numerical integration. Now, there have been several attempts to do that in the history of density functional theory, but we picked up on one that we found particularly elegant. And that is based on the work of Verpentinsky and Cook, and also later followed up by Dunlap and others in that work. And that is based on expanding the odd powers of the electron density, like rho to the 1/3 and rho to the 2/3, in terms of auxiliary exchange fitting basis sets. This is very specific for the Hartree-Fock-Slater or local exchange. So when you ask me, can I do B3-lib with it? No, you cannot. So far, you can only use the Hartree-Fock-Slater method. Where that will take us eventually, that's a different story. But it's a very nice, very clean, very elegant construction that is mathematically beautiful. And one thing you can do with that method is to choose a different alpha parameter for each atom in the molecule. And that is kind of cool, because we know that the alpha parameter that is optimal for carbon is different than the alpha parameter that is optimal for, say, xenon or cadmium. And so that is something that you can do. The method is very efficient. It is not quite as efficient in the SCF for solving the SCF equations, because there is a complicated nonlinear equation that you have to solve during the SCF. But everything else after the SCF is actually more efficient in ADFT than it is with numerical integration. So that is something that you can play with. You can do energies, analytic gradient, response properties, and excitation energies. And maybe that is something that has some bearing on what you can do with DFT in the future in ORCA. So the other thing is a rather serious theory that is something that is based on the work of John Perdue and was brought to chemistry early on in pioneering work by Philipp Furche, and that is the random phase approximation for the correlation energy. And that is something that is working with DFT orbitals, like for example PBE orbitals, but then is solving a different set of equations that gives you correlation energies, and these correlation energies are very, very good. And Andreas Görling and his co-workers, they have followed up on it. They have developed so-called zeta functionals, and they're among the best and most accurate functionals we know today. So we have a pilot implementation of the actual RPA method, and we have also evaluated it. Thermochemistry is very good. It's in the upper realm of what other functionals deliver, and it is kind of nice because it's very non-empirical. So it doesn't suffer from an overload of empirical parameters, and it is a physically very sound way to approximate DFT. This is just a pilot implementation, and we have every intention to follow up on it. I have to say it's a bit more expensive than than regular DFT, and it scales roughly as RIMP2 as we have it implemented today. Anyways, it's a very nice method. It's available only for energies, no analytic gradients yet, no density matrices, no excitation energies, but we're getting started on it. Yeah. Then something I think that was very important, and as ORCA has been getting powerful methodology like the Docker and the Solvator and the GOAT algorithm, it needed a cheap electronic structure method to be combined with for these hundreds of thousands of energy and gradient evaluations. And the method of choice is Stefan Grimme's XTB method, and that XTB method was always interfaced to Stefan Grimme's XTB code, and there's absolutely nothing wrong with that, and it's a wonderful program, very, very efficient too. And that interface will continue to exist in ORCA, of course. But we also now have a native XTB implementation that was done by Hagen Neugebauer. So he has created a native implementation of GFN1 XTB and GFN2 XTB, energy and gradients for GFN1 and energy for GFN2. And so that opens the door for much tighter integration with the ORCA infrastructure, and we look very much forward to keep exploring that further and help bringing XTB methodology to a broader group of users and computational chemists, and I'm sure many of you will be very interested in that. And so it's also beneficial in terms of performance because you don't lose time like writing data to disk, reading it again, starting a new executable, etc., etc. All of this is now native to ORCA. There are additional options and improvements in DFT that were mostly implemented by the Grimme group in Bonn. And so there are new keywords for double hybrid functionals. We have added various simple input options for libxc functionals because especially for the higher derivatives that is more reliable than the old ORCA native code. There is the B3lib 3C method, and I think that's important that the 3C methods that the Grimme group has developed and that are very extremely good bang for the buck in terms of like cost to accuracy ratio, they have been extended up to plutonium. There are also, I should mention that there are new options for computing CPCM terms in solvation. So the first option was always analytic, so using analytic electrostatic integrals, and these integrals, they had been reworked extensively for ORCA 6.0, and they brought major improvements in the speed of solvation calculations. And now we have experimented with alternative ways of computing these solvation terms, so you can do it by numeric integration, by the RI approximation, or also by multiple approximations. That is provided on an experimental basis, so we're not making this default. The default is still analytic integration, but it is something that if you find that solvation contributions may start to dominate the computation time, and that can happen for very large molecules, then there are alternative ways to deal with it that may or may not save you some time at the expense of introducing additional approximations and an error. Now let's take a look at what happened in single reference correlation calculations. And so there was extensive work by Giovanni Bistoni and his group. You know, he was here and now he's building up a very powerful group in Perugia in Italy. And they are focusing on intermolecular interactions, and they develop new methods in order to decompose these interactions to get chemical insight into the origin of these interactions. And he has provided, together with his group, a number of new methods, and there will be a talk later by Giovanni in this release event, and so he will explain to you in detail of the things that he's done with the ADL, the ADEX, the Covalent. The Covalent is then an energy decomposition that can cut in a physically correct way through covalent bonds, fragmentator, etc., and you hear much more about that if you just stay tuned after this talk. Now, here's a subject that is close to my heart, and where there has been a lot of debate. So it is unfortunate, in my opinion unfortunate, that in coupled cluster theory the T1 diagnostic is often regarded as a measure of multi-reference character to diagnose possible problems with a single reference approach. But the T1 diagnostic, I've been saying that for 15 years without anyone listening, then is anything but a multi-reference indicator. It does not measure that. And so it's good to look for alternative ways, and there have been many diagnostics, and I'm not dissing any of them. But we have implemented something together with Thomas Bondo-Pedersen and Fabian Faulstich that I believe is a very good indicator, and that is so-called S-diagnostic that Thomas and Fabian have introduced and that we have now implemented in the canonical branches of coupled cluster theory for closed shell and open shell Hartree-Fock. And I will just show you briefly how that works for a model system that I think is quite illuminating, and that is the difference between the Sidon peroxo dicopper complex and a bis-mu-oxo copper complex. So on the left side, on the peroxo side, you have two D9 open shell copper ions, each with one unpaired electron. So that is a singlet diradical, and by all means, that in coupled cluster language would qualify as a multi-reference system, whereas on the other side, you have two closed shell D8 copper ions, and that is a closed shell case. Now the T1 diagnostic tends to be small on the peroxo side, where it shouldn't be, and large on the peroxo on the bis-mu-oxo side, where it shouldn't be. So it behaves exactly the wrong way. It does indicate multi-reference character where there is none, and it does not show multi-reference character where there is some. And the S-diagnostic from Thomas and Fabian, it shows exactly the right thing. So it maximizes on the peroxo side, on the singlet diradical side, and it falls off steeply to the bis-mu-oxo side. So I think that is a much more reliable indicator of that situation than the T1 diagnostic. The T1 diagnostic measures like how bad Hartree-Fock orbitals are and like how much orbital relaxation you will have, and that is distinctively different from multi-reference character. So that is the S-diagnostic. And then we have implemented some things that are important for high accuracy thermochemistry for those users who are interested in obtaining insanely accurate numbers for small molecules. And so two things that have been missing here is the diagonal Born-Oppenheimer correction, and we have implemented that at the SCF level. And the second one is a spin-orbit coupling correction to the total energy. So there are many ways for doing that, for example, using the Darwin and mass velocity operator in perturbation theory. We have basically created something that can be viewed as a first-order perturbation approximation to a two-component SCF energy, and that provides a rough but valid estimate of the spin-orbit coupling contribution to the total energy. And you need that because we also have now implemented and will release higher order coupled cluster methods like CCSD full T and CCSD full T full Q to our users in the framework of the AutoCI generated code. And Ria Kayal has taken these methods. She has implemented the CCSD-TQ, and she has also then created a compound script that is implementing the heat protocol. And the heat protocol is something that was invented by Jürgen Gauss and the late John Stanton and their co-workers, and it's a very high accuracy protocol for extrapolated thermochemistry, so in the sub 1 kilojoule per mole. So don't try to apply that to your 150 atom molecule. That's not going to happen. But if you have a very small molecule of just a few atoms and a sufficiently powerful computer, this is a protocol that gives you very, very converged total energies that are within 1 kilojoule per mole of the best experimental energies. And now that's available in a very convenient way in terms of a compound script that does evaluate all of these thermochemical corrections. Now, let us turn to multi-reference correlation, and quite a bit has happened there in the multi-reference world in ORCA 6.1. And so the first thing, and you will hear much more about it, that's work by Benjamin Helmich-Paris, and he has implemented the CAST-DFT method. And that is, of course, something that is very attractive. So you get the static correlation from CAST-SCF and then the dynamic correlation from density functional theory. It's complicated to ensure that that it is not overcounting and everything is consistent. So it's a technically challenging implementation, but Benjamin has done that, and he has a paper that is, I think, currently under review, and he has graciously agreed to already give it to the ORCA users. And so that is something that we're excited about and that I think opens a whole new avenue of investigations with the combination of CAST-SCF and DFT. So stay tuned for Benjamin's talk. He will give you way more detail. The second thing is something that was actually requested by quite a few ORCA users, and that is to allow for the ORMAS module, and that is the occupation restricted multiple active spaces, and that's very similar to the generalized restricted active space concept. So it's a generalization of the RAS concept that can be used to partition the active orbital space into as many subspaces as you want, and then fix a minimal and maximum occupation within each subspace. So that has been implemented. It is available in the CAST-SCF module, but there also now is a standalone module that is called ORCA RAS-CI, and that is a very flexible CI program that can be used with extremely flexible CI expansion, and that also implements the ORMAS concept. So you can use it to either calculate global correlation energy, or you can use it inside an orbital window to create an approximation to full CI or whatever it is. So it's very flexible. It's also connected to the QDPT driver to calculate magnetic properties, and it is also connected to our OPA driver, the one photon absorption, to calculate excitation spectra. So that's a brand new module in ORCA that you can use for very flexible MRCI calculations. Don't expect wonders. In the process, we found out that our CI solvers will need a bit of TLC for larger orbital space, and by larger I mean like 100, 150, 200 orbitals that they don't handle very well, but that we hope to improve then in the near future so that these calculations get better and better. But it's definitely a very useful tool in the toolbox. Now the next work that was mostly done by Lukas Lang and in collaboration with Vijay Chakuri and myself, but really the heavy lifting has been done by Lukas, and that is to bring spin-orbit coupling and spin-spin coupling into the ICE method. So that is work that is very, very complicated. The paper is just now in press, and if you're not of the faint-hearted type, please check it out. It's extremely high quality theoretical work from Lukas, who has made this happen and has implemented it in ORCA, and now we give it to you, and and that means as a result you can do spin-orbit coupling calculations within the ICE method and also spin-spin coupling calculations with it. Here's a small example of the paper where Lukas studied the O2 molecule in the presence of spin-orbit coupling in near full CI quality and a decent basis set, and it matches the experiment beautifully down to the last detail. So that is something that we're excited about. That is some, in my opinion, very high quality theoretical work, and it is available now to you in ORCA. So, and the next thing, that is with our dear collaborator, Yang Gu, who we have worked with for I think close to a decade, and he does extremely high quality work in multi-reference theory and other very complicated areas of quantum chemistry. And he, together with Kanten, they have implemented now something that was on our wish list for a very long time, and that is the combination of a selected CI or ICE method with NeFPD2. So you can use now the ICE method to generate an approximate full CI solution for a large active space, and then use it in combination with NeFPD2. And in the paper that we published, I think we went close to 30 active orbitals. And that is a very significant step forward over the 14 active orbitals that are usually the limit. There are still very many technical challenges, and this is something that can and will be further improved, but we're super excited to give that to you, and it will, I believe, allow studies that just weren't possible before. Now, and then it's always a question like, what's the next? Like, how do you go better? And so we have given you multi-reference coupled cluster theory in ORCA 6.0. It's a very, very heavy lifting theory. But now we have explored a different avenue, and that is go to higher orders in perturbation theory. And our initial attempts here have led to an approximate NeFPD3 and NeFPD4 method. So NeFPD3 is implemented exactly, and NeFPD4 is implemented in an approximate way. But to our surprise, NeFPD4 confined to the voice, to the first order interacting space, is an incredibly great method. So it reaches almost the accuracy of multi-reference coupled cluster theory by being many, many orders of magnitude more efficient. So in fact, it is moderately more expensive than NeFPD2, but it reaches accuracy that goes a fair bit beyond NeFPD2 and almost close to MRCC. So that's a great method, and we will do much more with it in the future, and we look very forward to keep working on that subject. And that was work by Emily Kempfer again, together with Kanten Sivalinga. Very cool, please check it out. So finally, and that is also always something that is very close to our heart, and that is to not only produce numbers, we are committed to numbers, to accurate numbers, we are committed to efficiency, but at the end of the day, you always have to ask yourself, why do I want to do that calculation? What I'm going to learn about it? And so translating the results of these highly sophisticated calculations into chemical language that lets you have a chemical conversation with colleagues from chemistry is something that is extremely important to us. And so we had in 2012 introduced the ab initio ligand field theory that allows you to take the results of CAS-SCF NeFPD2 calculations and extract the ligand field Hamiltonian from it in a way that is unambiguous. And now it had one weakness, and that was the active space had to be the 5D-based molecular orbitals or the 7F-based molecular orbitals of the metal center. And that was no longer acceptable then, is because that leads to bonding that is too ionic, and it leads then to RACA parameters that are too large because that active space is just too small. And so now, based on work of Shashank Rao, we have extended this, and now you can use as large of an active space as you can afford in these ab initio ligand field theory calculations, as long as you include the 5D or the 7F orbitals. And the results that we have so far just on transition metal ions indicate that it fixes many of the problems that the ALFT had. And so that is something that we're excited about, that we're proud about, and that we plan to use much more in the future. So let me briefly talk about what we have accomplished in theoretical spectroscopy that has always been a mainstay of ORCA and something that ORCA was very much created for, and that's theoretical spectroscopy. So the first thing here is work by Thiago da Costa Gouveia and Dimitris Manganas. And so you know that we had in ORCA 6.0 given you the CSF ROHF method. So that's a method where you can converge the SCF to a spin eigenfunction even in the presence of complicated antiferromagnetic spin coupling. That was cool. And then we extended this to be applied in the configuration interaction framework. That led to the general spin-Roses method that can be used, for example, to calculate then X-ray absorption spectra of such antiferromagnetically coupled systems. But now we went one step further and also allowed for these methods to introduce spin-orbit coupling. So now that is the general spin-Roses method with spin-orbit coupling, and I think now it's a complete toolbox also to calculate, say, transition metal edges and other things for systems that have, many people would say, a multi-reference ground state. I would not say it's a multi-reference ground state. It's still a single configuration ground state, but with complicated, non-trivial spin couplings. And these spin couplings can be arbitrarily complicated. So whenever you can express a spin coupling as a single walk through the branching diagram, you can do these calculations. And that's pretty awesome. The application here is to XMCD spectra, and it does the job beautifully and picks up on the antiferromagnetic coupling concisely. Then something that we had that was requested for a long time, and that turns out to be quite complicated, and that is analytic Raman intensity. So that is a third derivative of the energy. And that is something that Petra Pikulova has worked through very meticulously and very beautifully, and it's a very efficient implementation of these analytic third derivatives that are required for the polarizability derivatives that give you the Raman intensity. And she will talk more to you about later, but she will show you that it is that you gain more than an order of magnitude relative to the numerical Hessian numerical polarizability derivative calculation, and I think that's a major achievement that people will use a lot. Finally, Marcos Casanova-Pace has worked tirelessly on open-shell STEOM calculations, and he has talked to you about already at the ORCA 6.0 release event, and he has now improved that further such that you can do core excited states with the open-shell STEOM equation of motion theory, and it's a very, very good method to calculate X-ray absorption spectra. And for those of you who will ask, is there a DLP&O version coming? Yes, there is a DLP&O version coming, but no, it is not in ORCA 6.1. But stay tuned, this is something that is very much on our horizon, and we're very excited to bring that to life, and Marcos is doing a phenomenal job on that. Now here, finally, after a long time, it's probably the most complicated property that ORCA implements, and that is the calculation of NMR and EPR properties based on CCSD parenthesis T wave function. It's something that Jürgen Gauss and John Stanton had pioneered in C4, and it's absolutely outstanding work that they have done there. And I've told you a lot about the AutoCI module and the code generator in ORCA 6.0, and work on the code generator is continuing tirelessly all the time. And because we have it deeply integrated, any improvement in the code generation chain will immediately profit everything that has been generated with it. But the other thing is also to not only improve the chain, but to implement exciting theories with it. And Hangzhou is not only arms deep into improving the code generation chain, but he has also taken it upon him to implement then these response properties with coupled cluster methods. And he has succeeded, and that is really fantastic work that he has done. And so because of that, we can calculate chemical shieldings in EPRG tensors with CCSD parentheses T wave functions. So that's something that's very exciting, and that I think is very much something that users of ORCA have been looking forward to. So finally, that's maybe a spectroscopic property, maybe it is something else, but I regard it as a spectroscopic property, and that is the spin relaxation time. So spin relaxation times are probably the part of paramagnetic EPR properties that have received the least attention, and that is for a good reason, because it's also the most complicated, but we became clearer and clearer that it's an absolutely central quantity for single molecule magnetism. And various people have started making various approximations, and usually the key ingredient is the geometric derivative of the spin Hamiltonian parameters. And that is usually done numerically, and many people have then resorted to, say, driving ORCA or another program from outside using external scripts. And what Sasha and Grau has now done is to write a whole ORCA module that is doing all of these things in a very controlled way, and in a convenient way, and in a user-friendly way, and in an efficient way. And he's working very intensely on the physics of the spin relaxation process. And he's giving you now the new module ORCA Mag Relax that is not only a standalone module, but can also be triggered from inside ORCA in order to predict spin relaxation times for you from whatever magnetic property calculation you are triggering, but specifically, of course, it is meant for the QDPT methodology in CAS-STF and FPD2. So very exciting work. There will be paper forthcoming that Shashank has written together with us, and we are very excited to give that to you too. Now, here's something I've already emphasized: the need to not only produce numbers, but also to gain insight into these numbers. And that is something that our friend Grégoire David has done. He has worked on that for several years, and it's very nice work. And that is the DFT exchange coupling decomposition. It is a so-called decomposition pathway. And what it can do is it calculates the exchange coupling, the Heisenberg exchange coupling, using broken symmetry DFT, but then decomposes it into physically interpretable contribution, namely the direct exchange, the kinetic exchange, and the spin polarization contributions. And that has many, many applications in molecular magnetism, and Grégoire has reworked his original implementation that was already in ORCA 5. Now it's fully documented, fully parallelized, fully there in ORCA 6, and we're very happy to give that to you too. Now there are a few improvements in ORCA that I would call quality of life improvements, and let's look at a few of those without going into too much detail. So there have been improvements in geometry optimization. In particular, for very large systems, sometimes you want to do these calculations in Cartesian coordinates, and that functionality has been improved. And there also is rigid fragment optimization, and that is something that Bernardo de Souza has done, and I think is very, very useful. TDDFT, there is an improvement. The TDDFT amplitudes are now stored in the GBW file, and that allows you to restart DFT calculations from an existing GBW file that contains TDDFT amplitudes. You can change the geometry, you can change the functional, you can even change the basis sets, and then it will still take these amplitudes as initial guess for the next TDDFT calculation. Finally, we have also worked on these shark integrals some more. There's a lot of stuff that has happened under the hood, but maybe for our users it is significant to know that now you can do all integrals up to an angular momentum quantum number of 10. I don't know who needs it. These are end functions. We also have streamlined in the process the nomenclature, because it's proper spectroscopic nomenclature, there are no J orbitals, right? So you go S, P, D, F, G, H, I, and then you don't go J, you go K, L, M, N. And that is the way ORCA is written now. So if you try to feed ORCA J orbitals, it will not accept it, right? So the proper L equals 7 is a K orbital. That is different from previous versions of ORCA, and you may need some adjustments in your input files if you're using that. There are more improvements. The JSON interface has been further improved, streamlined, tweaked, and you can now also get an AO basis fog matrix out of it, and even separate Coulomb exchange correlation, and CPCM fog matrices can be output into the JSON interface, and it is generally like more comfortable and more powerful than it was before, and I refer to the actual documentation for details. In localization, intrinsic atomic orbitals-based localization are now possible for virtual orbitals, and there are also additional options for the intrinsic virtual valence atomic orbital minimal basis sets. Thermochemistry has been extended to 100 temperatures available via input. That's also something that was requested in the forum, and so I just want to say we are reading this, we are listening to this, even if we don't always comply with everything, we're doing our best in order to cater to the requests from the user community. Yeah. There are additional ADM aliases for Axelrod Teller, type 3 body dispersion treatments, and other details. Especially also, and I think that was important, there were still a few problems with symmetry handling in ORCA 6.0, and the symmetry handling has been much improved. There's also a couple of new basis sets that you see here. I've flashed that up, but I will not read all of this to you. But we are constantly working on the basis set library, and now there are these, like, I don't know, 10, 15 new types of basis sets that you can request in the input file of ORCA. There are also improvements in compound, so compound starts to be really used by our user, and I'm very happy about that, because I think it's a very powerful, very convenient way in order to organize your calculations. In my own computational chemistry work, I use it all of the time, and Dimitrios Liakos, he's working on the compound implementation, and he has made quite some improvements, and again, details are in the manual. And by the way, the manual itself has massively improved because there is an HTML version now, and it has been completely restructured. That is heroic work by Markus Busch and Alexander Auer, and many of the group members have helped making that happen in order to give you the best documentation that we can possibly come up with. Final subject, unfortunately, programs have bugs. And programs like ORCA that consist of millions of lines of code, it's almost impossible to keep them bug-free, but we have very intensely worked on fixing the bugs that came to our attention. And so I will go very briefly through a list of bug fixes that we have done. So there were things in the SCF optimization, Hessian TDDFT, that weren't entirely smooth. For example, the CPSCF could be unconverged and would still continue. That is not desirable. That has been fixed. And there are many other things, like the RI trafo in CIPSI works now, MP2 with ANOs works now, UHF MDCI with conf works now, CPCM and MDCI respects max score, etc. And the new manual will have a comprehensive list of new features and bug fixes that were addressed. And so if you ask yourself, is the bug that I ran into previously, has that been fixed? And then you should look up this section of the manual. So there are a few more pages of things in bug fixes that we have done, and I don't think it's a good idea to go through them in excruciating detail at this point in time. I would only want to say we do care about it. We do care about giving you quality software, and we will continue to care about giving you quality software. All right, and so with that, I'm at the end of this introductory presentation. Please stay tuned. You have now opportunity to talk to the developers online, and then you will also hear more specialized talks, and I'm very excited about those too. So please stay tuned, stay with us, and have fun with ORCA 6.1. We had so much fun making it, and we are completely excited about what the future will bring for ORCA. But now, at this moment in time, please take ORCA 6.1 and go out in the world and do great stuff and solve chemical problems and enjoy. Yeah. Thank you very much. Bye.